Hello, my name is Luiz Inácio Proshnov, and I am the Brazil Program Director for the International Plant Nutrition Institute. And today, I'm going to talk with you about some myths and facts about the use of phosphorus in agriculture. Before going ahead, let me recognize my co-author, Dr. Norman Chien, who worked for years at the International Fertilizer Development Center. This presentation was given at the Sustainable Phosphorus Summit in August of 2018 in Brasilia, Brazil, and we have decided to record this presentation and offer to those with interest in the efficient use of phosphorus in agriculture. So what's our motivation to talk about this? We all know that phosphorus is one of the key nutrients for plant nutrition. We also know that fertilizer with phosphorus is generally seen as of low efficiency when compared to other nutrients, most especially to nitrogen and potassium. Now, due to the complexity of phosphorus soil reactions and the variety of P source options, many agronomic management technical issues are controversial. So this presentation will discuss some of these aspects related to the agronomic use of P in agriculture. And the model we have adopted is in the form of questions and answers. So we raise 7 questions and we present data and we conclude for each one of these 7 questions. First question is, may we transfer the sufficiency levels of P, which were obtained under conventional agriculture, to no-till? To explain about this, I'm going to use some ideas from Dr. Denardin from Embrapa Wheat in Brazil. So I adapted his presentation to make clear about this question. So let's suppose that we have conventional agriculture, situation A, and we have from 0 to 20 centimeters, we collect a soil sample from 0 to 20 centimeters, and as a result, by a given methodology, we have 10 milligrams of phosphorus available per kilogram of soil. Let's contrast this with a situation B, which would be no-till, where you have stratification of phosphorus in the depth 0 to 20 centimeters. In such a way that from 0 to 5, you would have 20, from 5 to 10, you would have 10, and from 10 to 20, you would have 5. Now, if you calculate in situation B, the average for 0 to 20, it would give you the same 10 as in situation A. So situation A is conventional agriculture, homogeneous distribution of phosphorus from 0 to 20. Situation B, no-till stratification of phosphorus as we give in the example. The question is availability of P in A the same as in B? And we don't believe, and the data shows that it's not, because in the no-till, you have a completely different situation in terms of soil reaction for phosphorus. You have more organic matter in the top soil surface. You have different soil fertility in the no-till or in situation B, which leads to different soil P reactions, different availability. So, considering calibration was developed for A, conventional agriculture, how to interpret results in B? Would we need to recalibrate for the new system? And we believe clearly as a conclusion that transferring the calibration, the sufficiency levels from A to B is not ideal. transferring the sufficiency levels from conventional agriculture to no-till is not ideal. The idea would be to calibrate the methodology again, simply because, as we said, the reaction of phosphorus, the situation is completely different under no-till as related to conventional agriculture. Second question we raise is, are high contents of P in phosphate rock for direct application desirable? You know, many think that because we have a higher content of P in a phosphate rock, that this would be interesting or desirable. So to explain this, we have data here for different phosphate rock sources, as you can see, in terms of the total P2O5 content. And you can see then from bottom to down, we have increased contents of total P2O5 in these different phosphate rock sources. Now, when we measure the PR reactivity, we see that the reactivity decreases from top to bottom. So that means as you increase the total P2O5 content in the phosphate rock, the trend is to decrease the phosphate rock reactivity. And the reason for that is because when you have higher content of P2O5 in the phosphate rock, you have lower substitution of this P2O5 by carbonate. And substitution of P2O5 by carbonate is essential to create instability inside the apatite crystal, leading to more solubility and higher PR reactivity. So as a conclusion, it is exactly the opposite. As you increase the P2O5 content in a phosphate rock, generally the trend is to decrease the solubility. So pay very careful attention to this. Question number 3 is it really necessary to always have high water solubility in totally acidulated P fertilizers? Generally, people believe that if you have a MAP, a monoammonium phosphate, or a diammonium phosphate, or a triple superphosphate, the higher the water solubility, the better. But the research, including some research that we have done in the past, does not give support to this conclusion. If you dig the information, you will see that there are water-insoluble compounds, water-insoluble P compounds in this totally acidulated P fertilizers that can be of very good performance, very good source of P to the plants. We don't have the time to show all the data. It's not our purpose, but you can always go and dig the literature seeking for this type of information. And as a result, I always pose the question, does not it sound funny that the fertilizer industry spends energy and money to transform phosphate rock, which has very, very low water solubility, in highly soluble P sources like single superphosphate, triple superphosphate, MAP, DAP, and then because these sources are too soluble, many try to somehow protect it for lower water solubility. So it means, again, you have a phosphate rock that has very, very low water solubility. Then you spend a lot of energy, a lot of money to transform this source into something that is very, very high water soluble. And because it's too water soluble, then you want to protect against losses in the soil system. Isn't that funny? Isn't there a more logical possibility? And we clearly believe that if you really produce the right totally acidulated P fertilizers, it is not always necessary to have high water solubility. So in conclusion for this question, not really. Adequate research should define the requirement for P water solubility for different sources and agronomic conditions, which will optimize the use of P resources. Okay, let's now talk about question number 4. And the question is P localized better than P broadcasted? Localized means inferred, and broadcasted means application on the soil surface. In many regions of the world, farmers are preferring to go from localized to broadcasted. And the reason is because they gain time. The operational facility is better when you broadcast than when you localized. Now, to address this question, there are 2 issues that we need to discuss. We need to discuss the agronomic implication and also the environmental implication related to this question. First, let's talk about the agronomic performance. I'm going to tell you some facts about this topic and related to this question. The fact number 1 is plant roots do not develop well in soil depths where P is low. I have seen this many times. You have soil availability of P high in the soil surface, but no available P inside the soil, plant roots do not develop. Fact number 2, water deficiency may happen in certain years. This is, of course, a fact. Everybody knows that. Now, fact number 3 is that with no roots developing into the soil, water deficiency may severely impact yields because the soil dries first in the surface. If you have roots inside the soil developing through the soil profile, even if the weather is dry, maybe you have water inside the soil, and if there are roots, the plants will not suffer so much. So these are the 3 facts. As such that depending on the interaction of factors, mainly soil P availability through the soil profile and climatic conditions, 3 things can happen. Most especially, 2 things can happen. Situation A, you set up an experiment to compare P localized or in furrow versus P broadcasted, and the result is that P in furrow performs better than P broadcasted. And this will happen in many situations because if the farmer applies P in furrow, he will have more availability of P inside the soil. And if there is water stress, these plants where you apply P localized will give better results than if you always apply P just on the soil surface, because of the reasons I explained it before. Now, if you do not have a water deficiency in a certain year, it doesn't matter too much if you apply the P localized or the P broadcasted. As long as you have a good availability of P on the soil surface, as there is no water stress, you will have P, you will have water, plants will develop well. So P localized and P broadcasted may perform exactly the same. Now, in some very specific situations, very rarely, you can have P in furrow performing worse than P broadcasted. But in general, we can concentrate only on the first 2 options. Now, besides taking into consideration the agronomic performance, we also need to discuss and to take into consideration the environmental implications. And I will tell also some facts about this related to the question above. The fact number 1 is that P runoff from the soil surface can affect water supplies, causing eutrophication. In many regions of the world, we do worry and we do have a problem of eutrophication of water bodies. This is an environmental problem. The fact number 2 is that applying P on the soil surface, of course, increases the chance for P runoff. And so, the fact number 3 is that eutrophication of water reservoirs will affect farmers in the long run. This problem will come after them, so we need to prevent this situation. So, in my opinion, generalizing broadcasting P on the soil surface or always on the soil surface may turn against the farming community in the medium to long run because of the possibility of increasing environmental problems. Okay, with that, agronomic performance, environmental implications, we can conclude, based on this question, is P localized better than P broadcasted? That not necessarily. Local conditions, especially soil profile and climate, will define the most adequate form to place P in the soil. Environmental implications do need to be considered on this equation. Okay, so now we go to question number 5. Can legacy P or the residual P be used as to decrease the future needs of phosphate fertilizer in the tropics? So the legacy P is the P that was not used by the plants and is still in the soil. So let's discuss a little bit about this. Agronomic practices exist in tropical regions that can recycle some legacy P into forms more available to plants. Some of these agronomic practices, or the main agronomic practices in this context, are: first, management of soil acidity with lime and phosphogypsum application. Yes, these practices can lead to more use of the legacy P. Crop rotation also can increase the use of the legacy or the residual P. And development or selection of plant species or cultivars with higher efficiency in recovering P from the soil. So these are 3 very important management strategies that can lead to more use of the legacy P in the soil. So in conclusion, there is no doubt techniques are available, others will be created to use more of the legacy P in the tropical regions. Of course, this will not eliminate the need for P addition in many circumstances. Question number 6. Does integrating grass and grain crops increase P availability in the soil system? I could use many of the available research data to answer this question, but I'm going to focus in the study done by Crucial and published in 2015, where they compared 2 situations. One is the monocropped corn versus the corn intercropped with palisade grass. And then, with time, they measure the concentration of the available P in different soil depths. And as you know the results, you can clearly see that more available P exists with time when corn was intercropped with the grass. So, the answer for the question is yes. And research should identify more adequate cropping systems for each region. Cropping systems that, among other benefits, will lead to higher amounts of available P. Question number 7, which is the last one, is phosphorus from fertilizers really less efficient than nitrogen and potassium? So let's discuss some facts. First fact is, we agree that phosphorus has very complex interactions with the soil system, and much of what is applied in terms of phosphorus can be converted to forms not necessarily readily available to plants. But the important thing is that the phosphorus generally stays in the soil system where you apply. Opposite to nitrogen and potassium, that are lost from the soil system much easier than phosphorus. Nitrogen can be lost by volatilization, a lot by leaching. Potassium can be lost a lot by leaching. So it's also a fact that the loss of P from the soil system is lower than nitrogen and potassium. Now, it's also a fact, as we have shown already, that not readily available forms of P can gradually become available depending on the forms of P, the length of time, the cropping system, the management, and the strategies. So what we are saying is, yes, phosphorus, a good part of the phosphorus applied is not readily available, but is not lost from the soil system. And if you use the correct agronomic practices with time, this phosphorus can be accessed by the plants. So in conclusion, not necessarily, in the medium to long run, phosphorus can even be more efficient than nitrogen and potassium. Some final comments. Please pay attention. Sometimes it is not what it seems. And of course, only science can provide the best alternatives. Be always skeptical with miracles. And be careful in changing dogmas, but don't be afraid to change if science points out in that direction. So with that, I thank you very much for your attention. I hope these questions and answers are helpful to your knowledge. And in case you have any doubt, you can contact me. You can find my email and other contact information at brazil.ipni.net. So thank you again, and bye-bye.